This is the 1 kilometer tall Jeddah Tower. But this isn't the skyline of Jeddah in Saudi Arabia. It's New York City. You see, the problem with the Jeddah Tower is that it is surrounded by a vast desert, making it very hard to get a true sense of scale. But when we put the Jeddah Tower in some of the world's most famous skylines, you can really appreciate just how tall this building is. Here's Shanghai, with the world's currently third tallest building, the Shanghai Tower. Next is Hong Kong, with its over 4,000 skyscrapers along the shores of Victoria Harbour. Chicago, with the Willis Tower, which was the world's tallest for 24 years. Sydney, and the iconic Opera House and Harbour Bridge. Kuala Lumpur, with its twin Petronas Towers, and the newly crowned world's second tallest, Merdeka 118. Toronto, whose CN Tower was the world's tallest freestanding structure for 32 years. Even in Dubai, it puts the world's current tallest building, the Burj Khalifa, to shame. So now that we understand just how big this tower is, we can talk about the incredible structural engineering that makes it possible. And we'll also be pushing the tower to its limits through some destructive simulations. By the way, this video took over 15 months to make. If you want to support the channel and help fund the creation of more documentaries like this, check out my Jeddah Tower t-shirt, which is linked in the description. It's the perfect Christmas gift for fans of engineering and architecture. Firstly, I'll provide a brief background on the history of the tower. It was designed by the Chicago-based studio known as Adrian Smith and Gordon Gill Architecture. Adrian Smith is best known as the architect behind the Burj Khalifa, the world's current tallest building. He designed the 828-meter tower while working at the firms Skidmore, Owings and Merrill, along with his colleague Gordon Gill. However, they both left the firm in 2006 to found their own eponymous studio. But the heroes of this story will be the structural engineers, specifically the firm Thornton Tomasetti, led by principal engineer Robert Sin. Thornton Tomasetti were responsible for the design of the Shanghai Tower, currently the world's third tallest at 632 meters. The contractor tasked with the Jeddah Tower's construction is the Saudi bin Laden Group. Rather surprisingly, this firm was founded by Osama bin Laden's father, Mohammed. The final important component of the team behind this building is Langen International, who are responsible for the investigation of the soil and rock conditions below the building and the design of the foundation. There has recently been a large amount of media attention on the Jeddah Tower due to the fact that construction recently resumed after being paused for several years. Construction first started in April of 2013. However, it halted in 2018 at a height of 63 floors, or 252 meters. It's rumored that the pause occurred due to the arrest of individuals involved with the construction contractor as part of the 2017 to 2019 Saudi Arabian purges. However, this has never been officially confirmed. The construction was also likely impacted by the COVID-19 pandemic. However, in January of 2025, Saudi officials announced the resumption of construction, almost 12 years after work first began. Estimates for the completion of the tower range from 2028 to 2029, which is a far cry from the original intended completion of 2018. This means that, in the best case scenario, the tower will take 15 years to build. For reference, the Burj Khalifa took 6 years to build, and the Empire State Building took a mere 13 months. That's a whopping 34 meters of height per month, compared to the Jeddah Tower's sluggish 5 meters per month. This highlights the incredible efficiency of skyscraper construction in 1930s America. Let's now get into the actual details of the tower. First of all, the official height of the tower is actually unknown. The Council on Tall Buildings and Urban Habitat, the world's leading authority on skyscrapers, simply lists the height as greater than 1,000 meters. The official project websites from both the architect and the structural engineer also list the same vague height. Theoretically, The height is kept a secret so that another developer does not decide to build an ever so slightly higher tower and steal all the glory. The height of the Burj Khalifa was also kept a secret until the official opening. However, given the Jeddah Tower's head start, it seems quite unlikely that any entity would be able to design, fund, and construct a multi-billion-dollar tower in a shorter time frame. The Burj Azizi, the Jeddah Tower's closest under-construction competitor, will be 275 meters shorter. Regardless, the unconfirmed height gives the Jeddah Tower an air of mystery. The model that we're going to explore in this video is 1,008 meters tall. This is based on drawings that have been released by the architect. But if you think you've got a better idea of how tall the tower will be, why not leave a comment and come back to it in 4 years and see if you are correct? The tower will be located in the Jeddah Economic City, which is a planned city located about 20 kilometers north of Jeddah. The development is part of the Saudi Vision 2030, which is the plan of the Crown Prince of Saudi Arabia, Mohammed bin Salman, to reduce the nation's economic reliance on oil as the world transitions to renewable energy. As of 2025, Sumoy Tower 1 is Jeddah's tallest building at a paltry 322 meters. Now that we've covered the history of the tower, we can get into the actual details. First, we'll get the obvious architectural features out of the way, and then we can peel away the facade and look at the internal structure. All things considered, the tower is rather unremarkable architecturally when compared to the jagged setbacks of the Burj Khalifa or the elegant curves of the Shanghai Tower. It's essentially an obelisk with a wide base that vanishes to nothing at the top. The slenderness ratio, that is the ratio of the tower's height to its base width, is 12:1. While this is rather slender, it's only half the slenderness of Steinway Tower in New York City, which has a slenderness of 24:1. However, the Jeddah Tower probably appears more slender due to its taper. When viewed from above, the tower appears as a Y shape with 3 distinct wings. One of the wings points directly at Mecca, Islam's holiest city, while another points directly north. The base width of the tower, used in the slenderness calculation, is measured along the axis of one of the wings, from the tip of one wing to the perpendicular bisector of the tips of the other 2 wings. The shape of the tower is a product of the client's requirements. Essentially, the client required that the tower be over 1,000 meters tall and that it would contain 240,000 square meters of usable floor area. The breakdown of this floor area is as follows. Levels 7 to 13 are office space at 10% of the total area. That's only 7 levels, so clearly only some of the world's most powerful corporations will be able to operate out of the world's tallest building. Levels 20 to 26 are 168 5-star hotel rooms at 10%. Levels 27 to 37 are 121 serviced apartments at 15%. A serviced apartment is basically like a hotel room intended for longer stays. Levels 44 to 120 are 318 residential apartments at 47% of the tower. That works out to an average of 4 apartments per level, although higher levels will have fewer apartments per floor due to the tower's taper. The final 18% of floor area from levels 126 to 153 is known as flex space. These levels are not currently allocated for any specific use, but they can be fitted out if the commercial demand is high enough. You'll notice we aren't actually at the top of the building yet. We'll get to that later. Scattered between the various sections of the tower are mechanical floors and refuge floors. Refuge floors, typically spaced about 20 levels apart, are used by occupants during an emergency evacuation due to fire or earthquake. Some occupants may be required to walk down over 500 meters of stairs, which is a physically exhausting task and potentially impossible for the disabled. So, The refuge floors allow occupants a place to rest and regain their stamina. Additionally, if a fire is contained in a small part of the building, it's not necessary for all occupants to exit the building. Thus, they can wait on the refuge floor until they've received instruction that it's safe to return to their office, hotel, or apartment. Refuge floors are fitted out with fireproof materials and are pressurized to prevent the entry of smoke from the stairwells. So adding up all the usable area, we get to 240,000 square meters, nearly 50% of which is dedicated to residential apartments. For reference, the largest skyscraper in the world by floor area is the recently completed Mori JP Tower in Tokyo. Finished in 2023, it has a floor area of 460,000 square meters, nearly double that of the Jeddah Tower, despite being less than a third of the height at 325 meters. This means that for every 1 meter of height, the Mori JP Tower provides roughly 1,400 square meters of floor area, while the Jeddah Tower only provides 240, nearly 6 times less efficient. So the Jeddah Tower is clearly very inefficient in terms of the floor area it provides for its immense height. But this is by design, because the vision of the client is to maximize the amount of floor area that's in the most desirable location, that is, being as high up as possible. Of course, the building could have just taken the form of a square extruded all the way to 1,000 meters. A square building with the same plan extent as the wing design would have a total floor area of 2.5 million square meters, over 10 times the actual floor area. First of all, the client didn't forecast that the residential and office rental markets in Jeddah would require more than 240,000 square meters of space. Therefore, they would see no point in constructing this additional floor area and being unable to generate revenue from it. Furthermore, with this rectangular massing, the target floor area of 240,000 square meters would be reached at a height of only 100 meters, meaning that offices and residences would have rather mediocre views. This would reduce how commercially attractive the floor space is, thus limiting the revenue the client could generate from leasing the space. So, the architect has employed a number of strategies to transfer floor area from the less valuable bottom of the tower to the more exclusive top of the tower. The first is by adopting the Y-shaped floor plan. The second is by tapering the floor plan with the building's height. A typical office floor at level 9 of the tower has a usable area of 3,700 square meters, while the penthouses near the top of the tower have a usable area of only 1,300 square meters, which is a 65% reduction. The final strategy is by cutting notches out of the floor plate to form balconies. The residential balconies are cut out of the curved facade that forms the transition between the wings of the tower. Having balconies on a building of this height is a rather unique feature. While the Burj Khalifa does have outdoor terraces, these occur at the locations of the setbacks, rather than being cut out of the side of the tower. And they have high glass barriers to prevent anyone from jumping off. This is not the case for the Jeddah Tower, where the balustrade could be easily mounted. In fact, if you look at a list of the world's tallest buildings, none of them have balconies like this, with most preferring to have an unbroken and smooth facade while maximizing the usable internal floor area. The architects of the Jeddah Tower give several reasons for the inclusion of balconies. The first is due to the supposedly pleasant weather conditions in Jeddah. However, with a daily mean temperature of 29 Celsius and a record high of 52 Celsius, most people would probably argue that these are not pleasant conditions. The second reason is to increase the appeal of the luxury residences in the tower. Obviously, the ability to enjoy the fresh air and breeze of a balcony increases the value of an apartment. And the final reason is that when the sun is high enough, the balconies have the effect of casting a shadow on the facade, which reduces the solar heating and improves energy efficiency. The balconies of the Jeddah Tower are also relatively simple to implement structurally, since they're formed by reducing the plan extent of the floors above the balcony and pulling back the facade line. This differs from a traditional balcony, which projects outwards from the building. Speaking of the facade, for simplicity, all of the glass panels are a standard 1.5 meter by 4 meter size, separated by stainless steel fins. These panels can be easily mass-produced and replaced. At 5 different levels of the tower, the facade is notched by 2 ventilation slots, which provide fresh air and allow exhaust from the various heating and air conditioning machinery within the mechanical floors. These slots are reminiscent of the iconic dark bands that were seen on the original World Trade Center. At a height of 670 meters, the 3 wings of the tower split into 3 separate spires, with each of these spires terminating very sharply at different heights. Just below the spire, at level 157, is perhaps the most unique architectural feature of the tower, the Sky Terrace. This circular platform cantilevers 30 meters from the side of the building at a height of 630 meters. Originally intended to be a helipad, it will now be used as a recreation and observation space after helicopter pilots believed it would be too dangerous to land a helicopter there. This glass floor observation deck will take the title from the current record holder, South Korea's Lotte World Tower, which has a 478-meter height. At the base of the tower is an expansive curved canopy that provides shade from the harsh Arabian sun to the undoubtedly luxurious vehicles that will be driving here. The canopy also shelters the 3 entrances to the tower, with each entrance servicing a different use of the tower, namely offices, hotels, and residential units. One negative effect of the convex-shaped tower facade is that it focuses sunlight with great intensity onto the canopy. A thermal simulation revealed that the top of the canopy could be heated to a maximum of 134 Celsius due to the sunlight. For reference, that's nearly hot enough to melt the metal indium, which becomes a liquid at 156 Celsius. While it may seem like a perfect opportunity to use solar panels on the canopy, the architects calculated that it would take between 8 and 20 years for the harvested energy to offset the additional investment, and thus it was not adopted. With all that said and done, we can finally strip away the facade of the tower and look at the internal structure. The logical place to start with is the foundations. Before the foundations can be designed, a comprehensive understanding of the site's soil conditions is required. This involved 11 boreholes, the deepest of which extended to 200 meters below the ground. This is the deepest borehole ever created for a building project in Saudi Arabia. Soil samples were retrieved from the boreholes and tested in a laboratory to determine the geotechnical properties, such as the strength of the soil and how much it would compress when being loaded. The following soil profile was established. The first 2 meters below the ground are sand. The next 50 meters are coralline limestone, which is formed from dead coral previously part of the Red Sea. Below the limestone, a 50-meter layer of weak sandstone is sandwiched between 2 gravel layers, before strong sandstone is reached at a depth of about 120 meters. This strong sandstone continues all the way to the borehole termination depth. The foundation system is known as a piled raft. This consists of a 5-meter deep Y-shaped concrete platform known as the raft, which is supported by piles below it. The raft is slightly larger than the footprint of the tower above it. The process of pouring this immense mass of concrete was quite complex, requiring significant formwork to hold up the hydrostatic pressure, in the same way that a dam wall supports the water behind it. In addition, when the concrete cures, it increases in temperature. It's critical to avoid temperature differences within the curing concrete, as this can lead to stresses being locked into the structure once the concrete has set. As such, the raft was insulated to prevent the extremities of the concrete pour from losing heat to the atmosphere, ensuring that they stay the same temperature as the center. 270 reinforced concrete piles support the raft. The circular piles are 1.8 meters in diameter at the wings and extend 45 meters into the earth. At the center of the raft, they're 1.5 meters in diameter and are 105 meters deep. In comparison, the Burj Khalifa has 192 piles, each being 50 meters deep. The fact that the Jeddah Tower's foundation is significantly larger is a result of it being a taller tower, and thus heavier, but also having worse soil conditions. The function of the piles is to transfer the loads from the building into the earth, and it achieves this in two ways. The first way is skin friction, where the surface of the pile interacts with the rough soil surface surrounding it, generating a friction force in the direction opposite to the applied load. A longer pile is able to transfer more load to the earth, since the surface area that interacts with the soil is larger. An everyday analogy for this is to imagine pulling a honey dipper out of a jar of honey. The honey grips the dipper and generates resistance. The other way piles transfer load is by end bearing, which is where the load is transferred directly to the solid rock at the base of the pile. The load transferred by end bearing is independent of the length of the pile, being influenced only by the diameter of the pile and the properties of the soil layer at the base of the pile. In the case of the Jeddah Tower, the engineers have actually ignored the contribution of end bearing to the pile capacity, when in reality, there will be a significant contribution. The result is a safe and conservative design with a high factor of safety. To verify the theoretically calculated pile capacities, 6 test piles were constructed and were then loaded by a hydraulic machine, with the downwards movement of the pile as it sank into the soil measured. Using the applied load and this sinking distance, the capacity of the test piles was experimentally calculated at 70 meganewtons. That is about 70% of the weight of the Eiffel Tower in a single pile. Remember now that there are 270 of these massive piles. Langen International, the project geotechnical engineers, developed a 3D finite element analysis model in the software Midas GTS. They modeled the soil layers to a depth of 200 meters within a 300 meter square area around the tower. Thornton Tomasetti, the structural engineers, provided Langen with the loads acting on the foundation due to the weight of the tower above. Through the use of the building analysis software ETABS, they calculated that the fully furnished tower loaded with occupants would weigh 8,800 meganewtons. This massive weight is hard to visualize, but it's about the same as 9 of the world's largest aircraft carriers, the USS Gerald R. Ford. But that's probably hard to visualize as well. So if we instead consider the blue whale, the world's heaviest animal, you're looking at about 9,000 specimens. The initial load provided by the structural engineers was based on an assumption that the foundation has a uniform stiffness. Given that the amount of load attracted to a part of the foundation is directly proportional to its stiffness, this means that the load was distributed evenly. However, in reality, certain locations of the foundation will be stiffer due to the interaction between the raft, piles, soil, and the structure of the tower above. The result is that certain parts of the foundation will attract more load than others. An analogy for this is to imagine a group of friends carrying a heavy couch. The stronger friends will naturally carry more of the couch because their body is capable of bearing more weight, while the weaker friends will carry less. The group of friends is the foundation, and the couch is the load. The stronger friends, being the stiffer part of the foundation, will thus attract more load. So the structural and geotechnical engineers engaged in an iterative process to accurately model the behavior of the foundation. This iterative process is needed because the geotechnical and structural engineers use separate models. The geotechnical model knows nothing about the structure above it, while the structural model knows nothing about the soil below it. The only shared factor between the two models is the load from the tower and the pile stiffnesses from the foundation. First, the load was applied to the geotechnical model, assuming a uniformly stiff foundation. The model outputs how much each pile sinks due to the load, known as the pile's settlement. The ratio between the load in a pile and its settlement yields the pile's spring stiffness. Each pile settles a different amount based on how stiff it is. Stiffer piles will settle less than softer piles. The maximum spring stiffness of the piles was estimated at 430 meganewtons per meter. For reference, that's about 15,000 times stiffer than the suspension springs found in a typical car. The spring stiffness can then be input into the structural model, which will then yield a new set of loads acting on each pile. The stiffer piles will attract more load, and the softer piles will attract less load. These updated loads are then reapplied to the geotechnical model, yielding updated spring stiffnesses. This process was repeated until the loads extracted from the structural model reached convergence and no longer changed. At the end of this iterative process, the settlements seen across the raft were quite uniform, which is a desirable result. If the settlements were not uniform, this is a state known as differential settlement, and it could cause the tower to lean to one side. Differential settlement is the reason for the Leaning Tower of Pisa's famous tilt. However, despite the minimal differential settlements seen in the Jeddah Tower, there was a problem with the distribution of the load. Remember that the loads in the tower were initially distributed evenly. After the iterative process, it was found that the loads in the walls at the tips of the wings had increased threefold, leading to these walls and the piles below them exceeding their load-bearing capacity. To rectify this, the piles at the center of the raft were lengthened to 105 meters from their initial length of 45 meters. The effect of this lengthening is to increase the stiffness of the center of the foundation, which would therefore attract more load, reducing the demand on the wings. The length of 105 meters was enough to even out the load distribution, but it was not long enough to bring the piles into the stiffer sandstone, which would have once again caused an uneven distribution. With the final foundation design, the settlements at the center and wings of the raft were estimated at 100 and 90 millimeters respectively. This differential settlement results in the tower leaning only 100 millimeters at the very top. This results in an angle of 0.006 degrees from the vertical, which is entirely negligible, especially when compared to the 4-degree tilt of the Leaning Tower of Pisa. The analysis also revealed that approximately 25% of the tower's load was transferred directly to the limestone below the raft, rather than going into the piles. However, to further increase the safety of the design, the piles were designed with the assumption that they took 100% of the tower load and that the raft contributed nothing. So, in conclusion, the foundation system of the Jeddah Tower is extremely robust and designed with a high factor of safety. A high factor of safety is particularly important for geotechnical designs due to the difficulty in accurately measuring the strength of rock and soil. Unlike man-made materials like concrete and steel, rock and soil are naturally formed and are inherently less homogeneous and predictable. Additionally, boreholes are unable to capture every detail of the soil profile beneath the foundation. They cover only a small fraction of the foundation's total area. So, the soil profile has to be interpolated between the boreholes. It's possible that the interpolated profile could be different to the actual profile. And if the actual profile is less favorable, this could lead to a reduction in the foundation's capacity. Now that we have a thorough understanding of the foundations, we can start to consider the above-ground structure of the tower. The vertical load-bearing system of the tower is comprised entirely of walls with no columns. This is quite atypical for a tall building. If we look at the floor plan of the Megatall 118, the world's second tallest building, you see a number of discrete columns distributed along the edge of the floor with an elevator core in the center. The same is true of the Shanghai Tower, which has a square core and a circular floor plate. The One World Trade Center also has a central core. While the Burj Khalifa might look quite similar to the Jeddah Tower, it also has columns at the ends of the wings. The columnless form of the Jeddah Tower is actually heavily inspired by Toronto's CN Tower, which was the world's tallest freestanding structure from 1975 until 2007. The CN Tower pioneered the wall layout used by both the Jeddah Tower and the Burj Khalifa, known as the buttressed core. A triangular or hexagonal core is located centrally in the tower, with 3 buttresses projecting outwards in the shape of a Y. A buttress is a structure that is built against a wall for the purposes of strengthening said wall and preventing it from falling over. You will see buttresses on many old cathedrals and temples. But why does it matter that the Jeddah Tower has no columns? Well, this is because columns and walls behave differently depending on the type of load acting on them. There are 2 main types of loads to be considered in the design of a skyscraper. The first are gravity loads caused by the weight of the building's structural materials, such as concrete and steel, as well as the weight of all occupants, furniture, and machinery within the building. Gravity loads act vertically. The second are lateral loads. These are loads that act horizontally and cause the building to move sideways. Lateral loads are primarily caused by wind and earthquakes. For a structure to adequately resist a load, it must be able to bear the load without exceeding its strength capacity and subsequently failing by buckling or fracturing. Additionally, it needs to bear this load without deforming excessively. When considering a building's ability to withstand loads, stiffness is crucial. A column excels at resisting vertical loads because of its axial stiffness. This refers to how well a structure resists compression or tension along its length. Axial stiffness is directly proportional to the cross-sectional area of a column. The fatter a column is, the more material it has along its length, and thus the more resistant it is to squishing or stretching. A column's axial stiffness is directly aligned with vertical loads, meaning it's able to utilize 100% of its material to resist the vertical load. However, columns do not have a high bending stiffness. Bending stiffness is the ability of a structure to resist loads that act perpendicular to its length, which in the case of a skyscraper are lateral loads. If we apply a load to a structure acting in a certain direction, the bending stiffness of the structure is proportional to how deep the structure is in the same direction as the load. In fact, in many cases, this relationship is not just linear. For example, the bending stiffness of a rectangular cross-section is related to the cube of the rectangle's depth. So, if you double the depth of a rectangle, you'll actually increase its bending stiffness by 8 times. Triple it, and you increase it by 27 times. So now perhaps you can see why a column is not great for resisting lateral loads. It does not have a large depth in the direction of lateral loads, and thus has a low bending stiffness. An easy way to think about axial and bending stiffness is to consider a ruler. If you grip 2 ends of the ruler with your hand and you try to push them together or pull them apart, you'll find that it's quite difficult. The ruler is using its axial stiffness to resist the load you apply. Now, if you take that same ruler with its long side facing down and you bend it, which is the effect of applying a lateral load in the middle, you'll find that it bends and deflects very easily until it probably snaps. This is because it has a low depth in the direction of the applied load. But by simply rotating the ruler 90 degrees, You increase its depth and thus its bending stiffness significantly, and it will be able to resist the load with minimal deflection and without snapping. This is where walls come in. Walls have a large depth in the horizontal direction and are thus perfect for resisting lateral loads through their high bending stiffness. At the same time, walls are also able to resist vertical loads, although not as efficiently as columns. As we explored previously, a typical skyscraper will use a combination of columns and walls to resist loads. Walls will typically be placed in the center of the building in a formation known as the shear core, which contains the elevators and fire escape stairs, with the columns distributed around the core. The core will resist the lateral loads as well as some of the vertical load, and the columns will resist the majority of the vertical loads. The columns will also attract a small amount of lateral load because their bending stiffness is not zero, but the sum of this load will be orders of magnitude less than the lateral load in the core. But why does the Jeddah Tower decide to only use walls? Well, in general, the lateral loads acting on a building are proportional to its height. This is because wind speeds increase with height, as the air is slowed down less by the rough surface of the earth. And the wind loads that act on a building are proportional to the square of the wind speed. So doubling the wind speed will quadruple the wind load. It's worth noting that for most tall buildings, wind loads are the most demanding lateral load. The exception to this is in seismically active regions like Japan, where earthquakes will govern. But what is the reason for wind loads typically dominating? The amount of acceleration, and thus force, experienced by a building during an earthquake can be modeled on what's called a response spectrum. This shows how the building's acceleration changes with its fundamental period. If you imagine the top of the building being pulled to one side and then let go, the fundamental period is the amount of time it would take for the building to sway in the opposite direction it was pulled and then return back. Another way to think of this is like a pendulum being pulled to one side, released, and subsequently swinging to the opposite side and then back again. The fundamental period is dependent on literally every aspect of a building's geometry and the materials of construction, but it generally increases with height. So a tall building will have a higher fundamental period than a short building. If we look at a typical response spectrum, you'll see that the acceleration has a sharp peak at low periods before reducing significantly for higher periods. Tall buildings will generally fall in the low acceleration region of the response spectrum and thus experience earthquake loads that are less intense than wind loads. So all of this was quite a long tangent, but we've established that the world's tallest building will experience some of the largest lateral loads ever existed by any structure. Therefore, the engineers wanted to ensure that every part of the building was working as hard as possible to resist the lateral loads, so they elected to use walls extensively. Additionally, walls are well suited to the tapering shape of the tower. If columns were used, the perimeter columns would either have to change position each level or be angled to match the taper. The first solution would result in the column load path being disrupted. Large column loads would be applied to the floor slabs rather than smoothly flowing to the column below. This is known as a column transfer, and it would require deep floor beams, which require more concrete and are thus more expensive. The second solution, known as raking columns, eliminates the need for transfer beams, but it introduces large bending moments into the columns. As discussed previously, columns don't have a high bending stiffness, and would therefore require expensive reinforcement. One downside of using walls instead of columns is that it does not lend itself well to having open floor plans, since the walls separate the floor plan into 3 distinct segments. Typically, tenants in high-end office spaces value an open floor plan that lets their employees move about with freedom. However, the segmented floor is perfect for the apartments and hotels that will make up the majority of the Jeddah Tower, where privacy and boundaries are essential. There are 4 distinct types of walls present in the Jeddah Tower. First are the walls of the triangular core. They are solid, straight walls that extend upwards for 2/3 of the tower's height. The triangular core contains the building's 59 elevators and allows for the circulation of pipes and ducts for plumbing, electricity, and air conditioning. An advantage of this large triangular core is that the elevators can exit directly into the space within the core, which acts as a lobby. In smaller elevator cores, the elevators exit outside of the core, which requires a penetration through the wall, reducing stiffness. The second set of walls are the corridor and fire stair walls, which act as the buttresses supporting the triangular core. The location of the doorways within these walls was driven by structural requirements to minimize the stress levels, so the architects had to organize the layout of interiors around this. At the end of the corridors, the space between the walls expands to allow the placement of fire stairs for emergency egress. Fire stairs are required at the ends of each wing to minimize the distance an occupant needs to travel to reach them. If the stairs were only in the central core, it would take far too long for an occupant in the wing to reach it, increasing evacuation times. The third set of walls are the transverse fin walls. At the base of the tower, each corridor and triangular core has 3 transverse fin walls to stabilize them, although these fin walls drop off with height as the tower tapers. In general, while walls are very stiff in the direction of their horizontal length, known as the in-plane stiffness, they lack stiffness in the perpendicular direction, known as out-of-plane stiffness, since they are much shallower in this direction. So these fin walls increase the out-of-plane stiffness of the corridor and triangular core walls, allowing them to cope with out-of-plane loads. Since each individual fin wall has a relatively small length, thus concentrating the load into a smaller area, they are the most highly stressed walls in the entire building. The final set of walls are the 3 wing end walls. These walls are positioned at the end of the corridor, closing the fire stairwell. They are similar to the transverse fin walls in that they stabilize the fire stairwells. However, they do not require any openings and are thus less stressed. The 3 end walls are inclined at slightly different angles, between 3 and 3.5 degrees. This may not seem like a large angle, but over the 670-meter height of the end walls, they move between 37 and 43 meters inwards towards the center of the tower, significantly reducing the size of the floor plate. Each of the walls mentioned has a different thickness at the base of the tower. That is, 1.2 meters for the transverse fin walls, 1 meter for the corridor walls, 850 millimeters for the end walls, and 800 millimeters for the triangular core. In general, since architects prefer thinner walls to maximize floor space, walls are only made thicker if they require this thickness for structural capacity or stiffness. So we can conclude that the thickest walls are under the most stress. With nearly 500 meters of total wall length at the ground floor, a thickness reduction of 100 millimeters would give an extra 50 square meters of floor space, yielding a significant increase in profitability. The wall thicknesses reduce at the quarter points of the non-spire height of the building, since as you go higher, the walls are less stressed. This is obviously due to the fact that there is less tower weight above the higher walls, and less obviously due to the fact that the stresses caused by lateral loads reduce with height. This second reason is because all skyscrapers can be simplified into a structure known as a cantilever, which is a beam with one end restrained from any movement or rotation, and the other end totally free. An everyday example of this would be a swimming pool diving board. The stresses in the cantilever are 0 at the free end, and maximal at the fixed end. The stress distribution between these 2 points depends on the exact loading, but for a uniform load across the cantilever length, the stress at any point is proportional to the square of the distance from the free end. This means that the stress halfway up the building is roughly a quarter of that at the bottom. In a similar fashion to wall thicknesses, The strength of the concrete used for the walls also reduces with height. The concrete used at the base of the tower has a compressive strength 30% higher than that used at the top of the tower. The high-strength 85 megapascal mix uses more cement and has better quality control than the 65 megapascal mix, making it more expensive. Thus, it's only used at the highly stressed bottom of the tower to reduce construction costs. For reference, the concrete used in a typical slab below a residential house or a driveway is only 20 megapascals. Each of the individual walls will be experiencing variable levels of stress depending on the direction and intensity of lateral loading. For example, if the applied load is aligned directly along the axis of one wing, the corridor walls of this wing will be highly stressed because their in-plane stiffness is able to be fully utilized. The corridor walls along the wings which are not directly aligned with the load will be less stressed, since their weaker out-of-plane stiffness is taking some of the load. Similarly, all other walls in the building will be at different stresses depending on how well they align with the load. This is where the coupling beam comes in. Their job is to link individual walls, providing a path for the load in heavily stressed walls to be redistributed to adjacent walls. Due to their small size relative to the walls they link together, coupling beams are some of the most heavily stressed elements in the entire building, and thus typically require dense steel reinforcement, sometimes up to 1,500 kilos of steel per cubic meter of concrete. This is around 10 times higher than the reinforcement seen in a typical wall. There are over 6,000 coupling beams in the entire building, with a typical depth of 1,500 millimeters. Almost every story in the building uses a constant 4-meter floor-to-floor height, which is rather typical for office buildings. Keeping the height constant allows the formwork used to cast the concrete to be reused many times, thus increasing construction speed and reducing cost. Additionally, this allows for generous ceiling heights in the tower's apartments, increasing the luxury appeal. Typically, a residential floor height would be closer to around 3 meters. We've mainly considered the walls as elements resisting lateral loads, but they're also responsible for taking the vertical loads of the tower's 250 floors. Typically, the floors of the Jeddah Tower are 250mm thick, two-way spanning slabs with no beams. The simplicity of this beamless design is beneficial for the speed of construction, requiring minimal formwork. The floors use reinforced concrete instead of post-tension concrete. Post-tensioning, the process of laying tension steel cables within the concrete, would allow for thinner floors, which would reduce the total weight of the building. However, in Saudi Arabia, the construction industry favors reinforced concrete since it does not require specialized labor and equipment to implement. For the first 670 meters of the building, the walls and floors do not change, with each level essentially being a carbon copy of the floor below, with the exception of some notches in the floors for balconies. However, at 670 meters, the structure of the tower changes completely. At this point, the inclination of the end walls has led to them intersecting with the triangular core. As a result, the floors have basically no commercially usable area. So any floors above this height are used only for mechanical purposes, and the floors no longer occur at 4-meter intervals. A 4-meter concrete slab, known as the sky raft, sits on top of the triangular core. The purpose of the sky raft is to act as a transition between the base of the tower and the spire. The wall layouts of the base and spire are different, meaning the load from the walls of the spire cannot flow directly into the walls of the rest of the tower. The sky raft, essentially an extremely stiff concrete slab known as a transfer slab, provides a load path for the spire loads to transfer into the base of the tower. In addition, the Skyraft also supports the building maintenance unit. The BMU is a crane which allows a cradle to be lowered down the building. Maintenance workers in the cradle are then able to clean the facade and replace any broken glass panels. It takes 3 months to clean the facade of the Burj Khalifa, so we can assume it will take at least that long for a building as high as the Jeddah Tower. The BMU can apply quite significant loads to the skyraft, since the cradle is being cantilevered outwards from the building and also being buffeted constantly by the wind. The end walls, which continue through the skyraft, are joined by new walls to form 3 closed silos for the remaining 330 meters of the building. This final 330 meters of height is known as the Spire, and it's the exact same height as the Eiffel Tower. The inside of the Spire is mostly empty, save for a few mechanical floors and an elevator for maintenance workers. The spires also contain 2 tuned mass dampers. A TMD is essentially a large mass, typically made of steel, which is suspended by cables and is able to swing like a pendulum. However, its movement is constrained by springs which link it back to the structure. When a lateral load is applied to the tower due to wind or earthquake, the tower will begin to sway at a rate known as its fundamental frequency, which we covered earlier. The TMD is designed to sway at the same frequency as the tower, but in the opposite direction, thereby absorbing energy and reducing the distance the tower sways. In other words, dampening the movement. The weight of the TMD is related to the height and stiffness of the building, and is thus said to be specifically tuned to achieve the required frequency. A taller building won't necessarily have a larger TMD. The 508-meter tall Taipei 101 has a 600-ton TMD. However, it's overtaken by the 435-meter tall Steinway Tower, which has a 730-ton TMD. Although the Steinway Tower is shorter, it's more slender than the Taipei 101 and thus less stiff, requiring a more massive TMD to prevent excessive swaying. The Jeddah Tower will have 2 TMDs, one 870 and one 260 ton. The TMDs are only required to limit sways in the spire, which is less stiff than the bottom 2/3 of the tower due to the lack of shear walls and floor slabs. However, the Jeddah Tower's 870-ton TMD is no match for the Shanghai Tower's 1,000-ton TMD, the world's heaviest, which has an elegant sculpture mounted on top of it. The functional part of the TMD, however, is just a flat steel disc. The final 50 meters of the tower are entirely steel, likely in the form of a lightweight lattice tower. This section of the spire would be too narrow for an elevator, so you'd need to climb a rather claustrophobic ladder to reach the top. However, it's unlikely that anyone would ever need to access the very top of the tower, save for maintenance workers replacing the aircraft warning lamps. Perhaps the only other visitors will be people like Tom Cruise and Will Smith to recreate their iconic photos from the top of the Burj Khalifa. The Sky Terrace is the Jeddah Tower's next major steel structure. It consists of 4 large beams which cantilever outwards a distance of about 30 meters from the central core. However, despite their great depth, these beams are not stiff enough to cantilever this distance without significant deflections. As such, they're supplemented by a truss that is about 30 meters deep, which effectively cuts the cantilever distance in half to 15 meters. A number of secondary beams radiate outwards in a circular formation from the primary beams, and they're positioned around glass apertures in the floor of the terrace. A footfall vibration is a common problem for lightweight steel cantilevers like this. Each time a person walking on the structure takes a step, they apply a small force to the structure. In the case of lightweight structures like cantilevers, the structure can begin to vibrate noticeably, causing discomfort for visitors and giving the perception that the structure is unsafe. This can become particularly problematic when the fundamental frequency of the structure matches the frequency of human walking speed, typically between 1 to 2 Hz, or steps per second. To combat this, a concrete topping slab is poured over the steelwork. This increases the mass of the structure and thus its ability to absorb energy from footsteps, thus reducing vibrations. You may be wondering why the Sky Terrace isn't made entirely out of concrete, since a heavy structure like this would remove any footfall vibration concerns entirely. The reason for this is likely due to difficulties in constructing a concrete cantilever like this. The contractor would need some way to prop the formwork that the concrete is cast onto, which is difficult when there's nothing below the sky terrace for 630 meters. Instead, the support truss can be assembled piece by piece, propagating outwards from the tower walls. Then, the main platform can be assembled at the ground level with minimal formwork, before being hoisted by steel cables to the final level and attached to the support truss, with the concrete slab cast as the final step. Let's now take a look at some destructive testing of the sky terrace. The first case we'll consider is a mass being dropped on the terrace from above. An example of this happening would be a crane dropping a bundle of reinforcement or plant machinery. If the object was dropped from the top of the building, it would fall approximately 370 meters, reaching a speed of 85 meters per second. As you can see, a 1-ton mass causes a slight vibration, but no permanent damage. With a 10-ton mass, we see some permanent damage, but the terrace remains attached to the tower. At 50 tons, the terrace stands no chance and is completely destroyed. The Mars M2480D can lift 330 tons, being one of the world's highest capacity tower cranes. Under a 330-ton impact, the sky terrace is completely obliterated. Given the sky terrace's original intended use as a helipad, we can also consider a helicopter collision. A typical 4-seat helicopter has a maximum takeoff weight of approximately 1,500 kilograms, with a top speed of around 220 kilometers per hour. You can see that the sky terrace is not impacted at all by such a collision, ignoring the effect of the helicopter exploding. Even if we increase the helicopter's mass to 10,000 kilograms, there's barely any damage. To destroy the sky terrace, we need to increase the helicopter's mass to an impossible 100,000 kilograms, 66 times heavier than the original helicopter. For reference, the Mi-26, the world's heaviest helicopter, has a maximum takeoff weight of only 56,000 kilograms. These results demonstrate the immense strength and safety of the sky terrace's design. The final case we'll consider is how many people would need to be standing on the sky terrace to collapse it. If a load is applied uniformly to the surface of the sky terrace, it would require approximately 3,600 tons to result in collapse. Considering an average adult weight of 80 kilograms, this works out to about 46,000 people, or 116 per square meter. It would be physically impossible to fit this many humans on the sky terrace, so a collapse of this nature is out of the question. Even if you filled the sky terrace with people standing shoulder to shoulder, you'd only fit about 1,900 people on it, or about 4% of the failure load. The final major steelwork component in the tower is the entry canopy. The canopy acts as the roof for 3 grand entry lobbies on each side of the tower. The ceiling height in these lobbies is approximately 25 meters. The main roof rafters are supported at one end by the tower, before spanning roughly 30 meters at a downward slope, at which point they're supported by a steel column integrated into the entry facade. Spanning between these rafters are secondary beams which support the canopy's architectural cladding. They're spaced to allow glass apertures, similar to the sky terrace. The canopy continues to slope downwards towards the tower's wings, extending a distance of about 50 meters from the tower end walls. The tips of the canopy are supported by 2 slender, architecturally clad steel columns, which gives the impression that the ends of the canopy are almost floating. Outside of its immense scale, the entry canopy is rather unremarkable structurally. The main complexity would likely be thermal expansion. As mentioned earlier, Thermal simulations revealed that the canopy could be heated to a maximum of 134 Celsius due to the focusing of sunlight. Given this, one of the 40-meter long rafters could be expected to be 50 millimeters longer at the peak temperature, compared to if it was only 20 degrees. Therefore, expansion joints would be required to ensure the structure can accommodate this movement without restraint, as restraint would cause additional stresses in the steel members, potentially leading to thermal buckling. This is commonly seen in railway tracks. Additionally, there is significant open space between the steel beams and the architectural cladding. The effect is that it forms what is known as a solar chimney. Solar radiation heats the air within the internal space of the canopy, causing it to rise and exit near the top of the canopy. Low-temperature outside air is then sucked into the canopy from the bottom. The result is that the steelwork of the canopy is constantly being cooled by fresh air, meaning it will be unlikely to ever experience the maximum temperature of 134 Celsius. Having said all that, now it's time to destroy the entry canopy. As with the Sky Terrace, we'll first consider the impact of a dropped object. A 1-ton object causes the column directly below it to fail. However, the canopy is strong enough to span the extra distance without this column. If we increase the object to 10 tons, the impact leads to significant collapse of the canopy, with multiple columns failing, although some of the steelwork is still able to cantilever from the face of the tower. Given the entry canopy's proximity to the road, it seems appropriate to simulate the effects of a vehicle impact. The truck you see here weighs 18 tons and is traveling at a speed of 100 kilometers per hour. The impact destroys 3 columns, resulting in the canopy sagging significantly. However, through a process known as catenary action, the canopy is able to span across this large gap without collapsing. It achieves this by going into tension, behaving in the exact same way as a chain hung between 2 points. It's important that structures are able to behave in this way to prevent total collapse from a single column failing. If you thought that simulation was a little underwhelming, we can decrease the strength of all the structural steel connections in the canopy by 75%. This produces a less realistic, although far more comprehensive collapse. And with that, we have covered every major structural component of the Jeddah Tower. To recap, we have the piled foundation, the triangular core walls, the corridor walls, the transverse fin walls, the end walls, the coupling beams, the floor slabs, the sky raft, the spire silos, the spire tip, the sky terrace, and the entry canopy. Now that you have a complete understanding of the building's structural system, you're ready to witness the ultimate destructive simulation. Without a doubt, the September 11 attacks against the World Trade Center represent the most devastating destruction of skyscrapers in history. The South Tower of the World Trade Center was impacted by a Boeing 767 traveling at approximately 950 kilometers per hour and weighing about 150 tons. The footage you're seeing now is a simulation of an aircraft impact of this scale occurring at the level of the sky deck. It's important, however, to cover a few caveats regarding the simulation. The first is that the simulation makes no allowance for an explosion due to the ignition of jet fuel. The second caveat is that the effects of heat from the burning of jet fuel are not considered. Although for a concrete building like the Jeddah Tower, the temperature effects would be less detrimental than for a steel building like the World Trade Center. Finally, the aircraft used in the simulation does not deform. It's able to transfer all of its kinetic energy to the tower while remaining as a single rigid body. In reality, the aircraft would crumple and disintegrate upon impact, reducing the amount of damage to the tower. Given all of these caveats, The simulations you're seeing are intended for entertainment purposes only. They give an idea of what an aircraft impacting the Jeddah Tower could potentially look like. However, they should not be used to draw conclusions about the safety or structural integrity of the Jeddah Tower. Regardless, the question of aircraft impact is an important consideration in the design of skyscrapers, particularly landmark buildings such as the Jeddah Tower. In fact, the World Trade Center towers were actually designed to withstand the impact of an aircraft, albeit an aircraft much lighter and traveling far slower than those that actually destroyed the towers in 2001. To recap this first simulation, we see that an aircraft strike at the level of the sky deck results in the Spire going into free fall, with its vast weight crashing into the levels below it. However, eventually the debris loses momentum and the collapse stops, leaving 470 meters, or just under half of the tower's original height, remaining. In this second simulation, the aircraft strikes at the base of the tower. This results in the total progressive collapse of the tower, forming a massive pile of rubble at the base. Progressive collapse is the process through which the failure of structural elements in a localized area results in adjacent elements failing, triggering a chain reaction which leads to the entire building collapsing. It's an example of the domino effect. As the top of the tower rushes towards the ground, it remains mostly unscathed, only disintegrating as it collides with the rubble pile at the base, having nowhere else to go. Rather surprisingly, the steel skydeck and the spire remain intact. The third and final simulation is the most interesting. Once again, the aircraft strikes the base of the tower. However, in this case, it strikes one of the wings of the tower, rather than directly at the center like the previous two simulations. This offset causes the tower to visibly lean to one side and split into two parts before it completely collapses. You'll also notice immediately after the collision, the back of the tower seems to spontaneously break apart, despite the fact that it is not hit by the aircraft. This is because the leaning of the tower causes tension forces to act on the back of the tower, thereby tearing apart concrete elements. The opposite is occurring in the front of the tower, where compression forces try to crush the concrete. And that brings us to the end of the tower collapse montage. The main takeaway should be that it is incredibly difficult to design a skyscraper to be robust enough to survive the collision of a fully loaded aircraft traveling at cruising speed. Once enough structural elements have been destroyed in the impact zone, the progressive collapse of the tower is almost inevitable. There simply does not exist a sufficient load path for the weight of the tower above the impact zone to travel to the ground. However, as stated previously, a simulation of this nature is very sensitive to how the aircraft deforms during the collision, and the deformation of the aircraft was not considered in these simulations. So keep in mind that these simulations are purely for the sake of entertainment. You might be wondering how the engineers performed all the design calculations and simulated the behavior of the tower. Additionally, how did the engineers have confidence that their calculations were accurate and their design was safe, given the fact that a building of this height has never existed before? The answer is that the structure was modeled in 5 different software packages, with each model being completed by a different engineer. Any major differences between the analysis results from these packages, such as the forces and deflections in the structure, would be cause for concern and would be investigated. Using different engineers also ensured that any user errors would be caught. The software packages used were ETABS, SAP 2000, Midas Gen, Strand 7, and Abacus. ETABS is perhaps the most widely used software package for analyzing complete buildings and has been used in the industry for 50 years. Midas Gen was specifically used for the vertical shortening analysis, which we'll cover later. Strand 7 and Abacus were used for advanced dynamic and stability analysis. The cost of the licenses for all of these softwares would be about $95,000, which sounds like a lot until you realize that the Jeddah Tower will probably end up costing north of $10 billion to build. For reference, the big cube you're seeing is $10 billion worth of gold, and the little cube you can barely see is only $95,000. Now, I want to go into more detail on the unique wind engineering behind the Jeddah Tower. I mentioned earlier that wind loads apply more force on the tower than earthquake loads, and this is best seen by comparing the base shear and overturning moments between the two load cases. The base shear is the lateral force acting at the base of the tower that would cause the tower to slide if it weren't for the resistance provided by the piled foundation. The Jeddah Tower's wind base shear is about 80% higher than the earthquake base shear. Similarly, the overturning moment, that is the rotational force at the base of the tower that is trying to tip the tower over, is about 50% higher due to wind than earthquake. So clearly the engineers need to focus on wind loads as the critical case during the design of the building. But how does one begin to estimate the wind loads of a skyscraper? Over many decades, researchers have developed technical standards that advise the expected wind loads on buildings based on wind tunnel tests of basic rectangular building geometries. However, these technical standards can typically only be used for buildings up to a height of 200 meters, since wind loading becomes less predictable after this point. So, for the Jeddah Tower, which is 5 times higher than this limit and also has an irregular Y-shaped geometry, these standards could not be used. Thus, the engineering team undertook custom wind tunnel testing for the Jeddah Tower. But what exactly is wind tunnel testing? In a nutshell, a scale model of the skyscraper is placed inside a straight enclosed corridor with a fan at one end. The fan accelerates air towards the model, and when the air collides with the model, it applies a force which can then be measured. The model sits on a turntable so it can be rotated, allowing the measurement of wind loads from any direction. However, the wind created by a fan alone is too uniform and does not accurately model the behavior of real wind near the Earth's surface, known as the atmospheric boundary layer. The Earth's surface is rough due to the presence of vegetation, buildings, and differences in topology. The result is that the wind near the surface of the planet is turbulent. That is, it mixes and swirls. As such, the wind speed increases with height, since the air is less affected by the surface roughness. To simulate these complexities in the wind tunnel, spires and blocks are used. Spires are tall triangular features at the start of the tunnel, quite close to the fan. Particles in the airstream are forced to go around the spires, increasing the distance they need to travel, thus reducing the wind speed. Since they taper with height, the spires disrupt the air less near the top, meaning the air particles move faster at the top. The blocks are small rectangular prisms placed on the floor of the wind tunnel to simulate surface roughness caused by buildings, terrain, and trees. When combined, these two simple shapes allow wind tunnels to accurately simulate the complex behavior of the Earth's atmosphere. The accuracy of a wind tunnel can be verified by comparing wind speed measurements to those collected in the real world with wind gauges or weather balloons. Now, of course, the model of the building used in the wind tunnel has to be far smaller than the actual height of the building. In the case of the Jeddah Tower, 4 separate wind tunnel tests were completed. The first used a 1 to 800 scale model, which gives a height of 125 centimeters. Measurements for this model were taken using the procedure known as high-frequency force balance. A force balance is essentially like a bathroom scale upon which the model sits, giving the lateral forces and moments measured at the base of the tower. The problem with the force balance is that it does not give any information about the distribution of loads along the height of the tower. The load distribution is essential to know how the building will move dynamically. If we return to the bathroom scale analogy, the weight measured by the scale will be the same if you are standing still on the scale or waving your arms around. This is where the second wind tunnel test comes in. Using a 1 to 600 scale model, a height of about 167 centimeters, this model was measured with high-frequency pressure integration. This involves the placement of hundreds of pressure sensors distributed along the surface of the model. The distribution depends on the geometry. For flat surfaces, the pressure sensors can be sparse. However, a higher resolution is required along edges and changes in geometry, since the wind behavior is more complex. The pressure measured by a sensor multiplied by the surface area of the model in the vicinity of that sensor, known as the tributary area, results in the force on the building at that specific location. The force from all the individual pressure sensors can be added together to give the total force and moment at the base of the tower. If the pressure sensor resolution is high enough, this should be close to the result from the force balance method. One problem with the pressure integration method is that each pressure sensor requires a tube to transfer the physical force of air to a computer to be measured and converted to a digital signal. While each individual tube has a small diameter, when you have hundreds of tubes, the space required quickly adds up, becoming a spaghetti-like mass which needs to be channeled through the base of the model. The internal volume of the spire in the 1 to 600 scale model was too narrow to pass all the pressure sensors through, so the team also tested a 1 to 400 scale model of the spire by itself, at a height of about 83 centimeters. Wind tunnel models are typically made from plastic or foams and can be 3D printed for more complex geometries. This massive 1 to 50 scale model of the top segment of the Burj Khalifa was actually made out of timber. All of the models discussed so far are rigid and do not deform. However, the deformation of the building can amplify the loads experienced by the building through a process known as aeroelasticity. So, the final model tested in the wind tunnel was a 1 to 600 scale flexible aeroelastic model. The materials and internal structure of an aeroelastic model are carefully selected such that the model has a stiffness similar to the real tower. This is typically achieved by integrating a metallic spine inside a hollow shell. As such, these models are the most expensive and time-consuming to create, and would typically only be used for complex and slender geometries when aeroelastic effects would be significant. Additionally, the aeroelastic model is only built late in the design stage when the architectural form of the building is locked in, since any major architectural changes would require the creation of a new, expensive model. The deformations of the aeroelastic model can be measured in a number of ways, including using lasers. The measured values can then be used to verify those calculated in the analytical model. The behavior of a building under wind loading is heavily influenced by a building's fundamental periods of vibration. I mentioned earlier that the fundamental period is the time taken for the building to complete a single oscillation when a dynamic load is applied, essentially like a single swing of a pendulum. However, this fundamental period is actually just one of an infinite number of different ways the building can oscillate, known as modes. The structure can oscillate by translating or rotating in any direction. The fundamental period is the first mode and has the longest period, with subsequent modes having shorter periods. Furthermore, not all of the structure participates in the oscillation of a certain mode. Certain parts of the structure will not move at all. The ratio of the mass of the structure that is moving within a certain mode divided by the total mass of the structure is known as the mass participation factor. The mass participation factor is also highest in the first mode and decreases subsequently. This means that we're only interested in the first few modes, where the building is translating or rotating as a single unit in a clearly defined direction. Typically in higher modes, only a few flexible slab edges or walls will be moving, and this does not have a significant impact on the performance of the building as a whole. In the case of the Jeddah Tower, the first two modes are translation along two of the Y-shaped axes of the building at 11.9 and 11.2 seconds respectively. For reference, the Burj Khalifa's first mode is translation with a period of 11.3 seconds. Since the fundamental period is directly proportional to a building's height, the fact that the Jeddah Tower is 20% taller than the Burj Khalifa, but has a first mode period only 5% longer, is a testament to the stiffness of the Jeddah Tower. The third mode of the Jeddah Tower is torsion at 5.8 seconds. Torsion is rotation about the tower's vertical axis, otherwise known as twisting. The behavior of a structure under torsion is less understood than the behavior under simple translation, so there is less confidence in the ability to achieve a safe design. In addition, concrete under torsion requires a larger amount of steel reinforcement to prevent cracking and subsequent loss of stiffness, when compared to concrete experiencing simple bending forces resulting from the translation of a building. As a result of these two complications, concrete elements that must resist torsion are more difficult to design and more expensive to construct. Therefore, the structural engineers of a building will always endeavor to ensure torsion is not present in the first two modes of a structure. Torsion only appears in the fifth mode of the Burj Khalifa, with a period of 4.3 seconds, suggesting it has a higher torsional stiffness than the Jeddah Tower. Now that we've covered the modal behavior of the tower, we can consider its distinctive Y shape, which is beneficial in reducing wind loads. Consider a building with a rectangular profile. When wind strikes the front face, it wraps around the corners of the building and continues along the side faces, before separating from the surface of the building at the back face. At this point of separation, swirling vortices form, which creates areas of negative pressure, and a suction force, which pulls the building towards these areas of negative pressure. So, the front of the building is being pushed by the wind, and the back is being pulled. Both of these forces are acting in the same direction, and the result is that the total wind force, and thus movement of the building, is greater. So, if you can figure out a way to prevent these vortices from being formed, the wind loads on the building can be reduced. The simplest way is to give the building a streamlined profile, like a helmet used by cyclists in the velodrome. The long tail of this profile ensures the wind cannot separate from the surface and create the vortices which would increase drag. The Y-shaped profile of the tower deals with vortices in a different way. We can consider two cases of wind interacting with the tower. The first is wind striking directly in line with one of the three wings of the tower. In this case, the air splits evenly between the two sides of the tower, traveling along the facade before being redirected by the two other wings. When the air separates from the tower at the end of the wings, It's now pointing about 10 degrees away from its original direction. The vortices that form are no longer aligned with the original wind direction. This means that the magnitude of the suction force on the back of the building in the original wind direction is reduced. Additionally, since the vortices form on opposite sides of the building and the suction forces are directed away from the building, the vortices on either side tend to partially cancel each other out, resulting in less overall suction force. The second wind case to consider is wind striking in the concave region between the two wings. In this case, the air becomes temporarily trapped in the concave region before moving backwards against the wind flow direction and wrapping around the ends of the wings. When the air separates from the wings, it is once again angled differently to its initial direction, resulting in a reduction in the suction force. However, this building orientation is less aerodynamic than the first case due to the large force that is applied to the building when the air is forced to move backwards. Jeddah, along with much of the Persian Gulf, is subject to a strong north to northwesterly wind known as the Shamal. The Shamal wind is the strongest wind experienced in Jeddah, so the tower is oriented such that one of the wings is directly aligned with the north and thus the Shamal, allowing the building to perform more favorably than if one of the concave faces was aligned with the Shamal. The tapering form of the tower also reduces the impact of wind loading by interrupting a process known as vortex shedding. This is where the vortices on either side of a building form out of phase with each other. As the building is pulled towards these regions of negative pressure, it will oscillate from side to side. This becomes a problem when the oscillations due to vortex shedding match the building's natural frequency. This is known as resonance, which is the same process occurring when an opera singer shatters a wine glass with their voice. Resonance causes the lateral forces on the building to be amplified, and this can lead to excessive swaying, causing discomfort for occupants and even overstressing the building's structure. By tapering the building, the rate at which vortices are formed varies with the building's height, since the building's cross-section is constantly changing with height. This means that vortices will no longer be formed purely on only one side of the building at a time. They will form on both sides of the building at the same time, thus cancelling each other out and ensuring the building will not sway to a problematic degree. The Burj Khalifa also took advantage of a taper to reduce wind loading, although the tapering happened at discrete points known as vertical setbacks, rather than a continuous taper like the Jeddah Tower. Bill Baker, the Burj Khalifa's structural engineer, referred to this tapering as confusing the wind. The result of these numerous aerodynamic optimizations is that the Jeddah Tower experiences wind-induced accelerations at the highest occupied floor that are half of the maximum limit for the comfort of occupants inside the building. For the strongest wind event that can be expected to occur once in a typical year, the expected acceleration is only 6 milli-Gs, that is, 0.6% of the vertical acceleration experienced on Earth due to gravity. The majority of occupants in the building would not even notice this. This acceleration would certainly be less than that experienced in Chicago's Willis Tower, which has filing cabinets that can be seen to noticeably slide on their rails during a windy day. During a 1 in 50-year wind event, the top of the tower can be expected to move about 1.7 meters. This may seem like a lot, but this corresponds to a sway of about 1/600th of the building's 1,000-meter height. Typical limits for the wind-induced sway of a building during a 1 in 50-year storm would be about 1/400th of the height, or about 2.5 meters. So once again, the Jeddah Tower is exceeding the requirements for occupant comfort. The final unique consideration for the world's tallest building is addressing the problem of vertical shortening. Vertical shortening, as the name suggests, is the process by which the entire tower reduces in height due to its immense self-weight over the course of many years. It may be surprising, but even thick concrete walls will compress a slight but measurable amount if the load applied to them is high enough. There are 3 main components of vertical shortening. The first is elastic, which happens immediately after the load is applied. If the load is removed from the wall will return to its original height. This is similar to pressing down on a sponge. The sponge will spring back to its original shape when the load is removed. The second component is shrinkage, which occurs as the concrete loses moisture to the atmosphere and dries out after it sets, thus contracting. Imagine a piece of fruit being dried in an oven. Shrinkage occurs in the concrete regardless of whether or not it is loaded, and it is permanent. The final component is called creep, which is the time-dependent deformation that occurs in a material when subjected to a sustained load. Imagine a bookshelf loaded with heavy books. While the shelf will sag initially due to the weight of the books, over many years, the sagging will increase even if the weight of the books on the shelf has not changed. Unlike elastic shortening, the effects of shrinkage and creep occur over many years. Generally, they follow a logarithmic curve, with the majority of the shortening occurring in the first few years of the structure's life. However, engineers will still consider the effects of shrinkage and creep shortening for the entire life of the structure, which may be up to 50 years. Shrinkage shortening will begin as soon as the concrete has been cast, while elastic and creep shortening only begin once the concrete has been loaded. In a typical building, creep will account for about 60% of the vertical shortening, with shrinkage and elastic accounting for about 20% each. However, this distribution is highly variable and depends on many factors, such as the strength of concrete, environmental temperature and humidity, and the time of loading. Time of loading is the critical factor, and the easiest way to reduce vertical shortening is to give concrete as much time as possible to gain strength before it is loaded. Concrete strength over time follows a logarithmic curve, with about 40% of the final strength being achieved after 3 days, 70% after a week, and 90% after a fortnight. Full strength typically happens at 28 days, with marginal increases beyond that point. So, the longer you wait before applying load to the concrete, the stronger it will be, and thus it will experience less vertical shortening. However, this is easier said than done. The average time to pour a single story of the Jeddah Tower is about 5 days, after which the next story will be poured, thus loading the story below it. That is to say, the concrete in the Jeddah Tower is being loaded after about 5 days. If you were to double this loading time to 10 days to reduce vertical shortening, you would double the construction time of the building. It's important to note that there is a lag between the time the walls and slabs are poured, generally about 5 stories. This allows a wall to be about 25 days old when the heavy load of the slab it is supporting is applied, thus reducing vertical shortening. In addition, you'll notice that the core is about 7 stories ahead of the wings. The reason for this is to ensure that the concrete of the core and the wings are poured separately, allowing them to shrink individually rather than as one giant mass, reducing the amount of shrinkage cracking. So now that you understand what vertical shortening is and what causes it, you might be wondering why this is a problem. Well, there are 2 main issues that arise from vertical shortening. The first is differential vertical shortening. If one region of the building experiences more vertical shortening than another, this will result in the floor levels of the building being uneven, which causes issues for occupant comfort, as well as potentially damaging brittle architectural finishes like glass. If you imagine a glass window, if the floor below one side of the window sinks more than the other side, eventually the bending stresses induced in the glass may cause it to shatter. The fact that the Jeddah Tower's vertical support system is composed entirely of interconnected walls helps to reduce the effects of differential vertical shortening. The coupling beams ensure all regions of the building are linked together, and are thus able to restrain each other from differential vertical shortening. If one wall in the building begins to shorten more than its neighboring walls, it will be restrained by said neighboring walls, which will experience an increase in stress as they act to prevent this initial wall from shortening. Differential shortening is more so a problem in traditional skyscrapers consisting of a central core with columns surrounding it. The columns, which have a small cross-sectional area compared to the core, will tend to undergo more vertical shortening than the core. However, the only thing linking the columns to the core is the thin floor slab, which does not have sufficient stiffness to restrain the columns from shortening in the same way that the coupling beams do. Even if differential vertical shortening has been solved, a second challenge remains. That is the fact that once all of the vertical shortening has occurred, the tower will be measurably shorter than it was at the end of construction. You can't claim to have a 1 kilometer tall tower if it has shrunk by several hundred millimeters. So, the vertical shortening is corrected by making all the vertical concrete elements for each story slightly taller than they need to be. This process is known as cambering. If the engineers calculate that a story will shorten by, for example, 100 millimeters, the construction workers will make all of the walls in that story 100 millimeters higher than the intended floor-to-floor height of 4 meters. This means that after vertical shortening occurs, the walls will be exactly 4 meters tall. If this extra height was not allowed for during the pouring of the concrete, then the final wall height would be less than 4 meters. An additional complexity is that every story shortens by a different amount based on the weight of the tower above the story, the time the story is poured in the construction sequence, and the thickness of the walls supporting that story. A story at the base of the tower is going to shorten more than a story near the top of the tower, since there is so much more load at the base. This means that if you did nothing to rectify the vertical shortening, the floor-to-floor height would be slightly different for each story. As such, a unique facade glass panel with the correct height would need to be manufactured for each story, which would be an expensive and inefficient process. It's much cheaper to correct for vertical shortening and ensure the floor-to-floor height for all stories is exactly 4 meters high, allowing the mass production of thousands of 4-meter high facade panels. Mass-produced panels of uniform dimensions are significantly cheaper to manufacture and install than custom panels. Even with mass-produced panels, the facade of the Jeddah Tower is estimated to cost well over $100 million, highlighting the importance of minimizing this cost. The structural engineers of the Jeddah Tower have publicly released graphs showing the calculated vertical shortening of the tower at the end of construction at the center of the tower. The shortening is plotted relative to the tower's base, which is taken as the fixed reference point. So while the lower stories do undergo the most compression, the base itself is defined as 0 in the graph. The plotted values are also corrected, meaning they reflect the predicted final profile of the tower after cambering, not just the raw uncorrected shortening. Because of this correction, the displacement does not simply accumulate with height. Instead, the maximum deformation occurs at a height of around 400 meters, reaching approximately 230 millimeters. While 230 millimeters of shortening may seem like a lot, given the tower is 1 million millimeters tall, the deformation amounts to only about 0.02% of the tower's total height. Breaking it down, creep is the largest contributor, followed closely by elastic shortening, with shrinkage playing the smallest role. Finally, you'll notice the abrupt jump in shortening at about 670 meters. This corresponds to the 4-meter thick sky raft, which is so stiff that it undergoes almost no shortening. The accuracy of a vertical shortening study is extremely dependent on the assumptions made about the duration of construction. For example, the engineers originally assumed that each story would take 5 days to complete. So the fact that there's been a 7-year pause in construction would completely invalidate the results of the original vertical shortening study. This is likely one of the biggest challenges facing the engineers as the building resumes construction. Elevation measurements would need to be taken at every single story in the building to determine the extent of vertical shortening that has happened since the construction began in 2013. The engineers can then take these measurements and update their original vertical shortening model to account for the 7-year pause in construction, yielding new camber values for all of the wall elements. Construction would need to be closely monitored to ensure that the 7-year pause does not create any unexpected behavior in the vertical shortening of the building. After all, there are few examples in history of a building that has resumed construction after such a long pause, let alone a building that is already 250 meters tall. So this is totally uncharted territory from an engineering perspective. Another concern is the fact that the forces applied to structural members are also dependent on the construction sequencing and will constantly change as construction progresses, and even for years following construction. As seen in this graph provided by the engineers, the shear force in this coupling beam at level 40 is about 1400 kilonewtons at the end of construction and increases by 25% to 1750 kilonewtons after 16 years. This is a significant increase, and this coupling beam would have to be designed for the maximum load, despite the fact that it will not occur for many years following construction. Due to the complexity and scale of this building, it's impossible to predict what impact the 7-year pause in construction will have had for the time history of forces in all structural members. It's very possible that some members may experience a force higher than what they were originally designed for. This is not a problem for any members that have not been constructed yet, since they can simply have their dimensions increased or be given additional reinforcement to increase capacity. It is, however, problematic for members that are already built. They will need to be reinforced using expensive and time-consuming post-construction techniques, such as the bolting of external steel plates, carbon fiber wrapping, or the casting of a new concrete jacket around it. The final concern arising from the pause in construction is that of concrete durability. The design of concrete members is heavily influenced by the environment it is exposed to during its design life. The walls and floors of the Jeddah Tower would likely have been designed for an internal, air-conditioned environment. Such an environment has low humidity, low salinity, and a controlled temperature. This environment is only possible once the facade has been placed and the internal concrete structure is fully isolated from the outside atmosphere. However, for the past 7 years, there has been no facade on the Jeddah Tower, and of course no air conditioning. As a result, the concrete members have been exposed to the harsh temperatures and salinity of the Saudi Arabian desert and the Red Sea, not to mention frequent sandstorms. This is a problem because concrete designed for an internal environment would struggle in terms of durability in an outdoor environment. The two most important factors for the durability of concrete is the cover to reinforcement and the reinforcement ratio. The cover to reinforcement is the distance from the external face of the concrete to the closest steel reinforcing bar. With higher cover, there is more concrete to form a physical barrier that protects the steel from chlorides found in salt, which would corrode the steel. When the steel corrodes, forming rust, it can expand and exert pressure on the concrete, which results in chunks of concrete breaking off from the member. This process is known as spalling. Additionally, parts of the corroded steel can also break off. Both of these mechanisms will reduce the capacity of the concrete structure, potentially leading to structural failure. The second factor of importance is the reinforcement ratio, which is the ratio between the cross-sectional area of steel compared to the total cross-sectional area of the concrete member. With a higher reinforcement ratio, the concrete will experience less cracks, and the cracks that do form will have a narrower width. Narrower cracks inhibit the ingress of moisture and chlorides into the concrete, preventing corrosion. So, the potential problem is that the walls and floors of the Jeddah Tower do not have sufficient cover and reinforcement to handle the severe outdoor conditions they've experienced for the past 7 years. Typical cover for an internal concrete member may be in the order of 20 millimeters, compared to 50 millimeters for an external member in saline conditions. It's likely that the engineers will have to take samples of the existing concrete members to be tested in the laboratory to determine if there is a risk of corrosion to the reinforcement. An example of one such test is the carbonation test, where a special chemical is applied to the concrete. A healthy sample of concrete will react to the chemical and turn pink, indicating it's not at risk of corrosion. So with that, we've covered basically everything there is to know about the Jeddah Tower. Despite its record-breaking kilometer height, we've come to learn that the structure of the tower is actually relatively simple. Just flat concrete floors supported by a Y-shaped system of concrete walls that transfer loads to the earth through a deep piled foundation. The most unique part of the structure is perhaps the cantilevering steel observation deck at 630 meters. In fact, it's a stretch to even call the tower 1,000 meters tall. A third of it is just a hollow, uninhabited spire whose sole purpose is to reach this arbitrary height. Perhaps you could even argue that it is unethical for such a tower to be constructed, given how many workers will inevitably die during construction, not to mention the millions of lives that could be lifted from poverty if the billions of dollars spent on construction were diverted to charity instead. However, I will leave those philosophical discussions for others. In any case, the story of the Jeddah Tower is not over. There are numerous challenges to overcome after the resumption of construction following a 7-year pause, not to mention a complex construction process at heights that humans have never worked at before. Some might even argue that the tower will never be completed, as Saudi Arabia shifts its focus to other mega projects such as NEOM. Only time will tell. Before we finish, I want to highlight the main sources used to research this video. The first is an excellent 2020 presentation given by Robert Sin, the tower's principal structural engineer. The second is the 2022 book titled Supertall, Megatall, How High Can We Go?, which has an entire chapter dedicated to the Jeddah Tower and features floor plans, elevations, and renders of the building. That concludes this documentary on the Jeddah Tower. If you'd like to support the channel, please consider subscribing and checking out my Jeddah Tower t-shirt linked in the description. Thank you so much for watching.